You strike the pavement, a shock wave travels up your leg, and an exact number updates on your wrist. It feels like a simple, direct transaction. But that device doesn't actually see your foot hit the ground. It is entirely blind. All it receives is a chaotic stream of physical force data that it must interpret in real time. To capture that force, the watch relies primarily on an accelerometer. This sensor measures linear movement, specifically the vertical up and down bounce created every time you move. The problem is that the accelerometer only understands linear force and abrupt physical shocks. It has no concept of the space around it or your body's orientation. When a device relies strictly on vertical bouncing to count steps, the data is highly vulnerable to false positives. The watch needs more context because the world is full of movements that look exactly like walking to a blind sensor. Consider the vibrations radiating through a steering wheel when you drive over a potholed road, or the erratic, repetitive arm movements involved in scrubbing a pile of dishes. Even the rapid, percussive strikes of your fingers typing out an email create intense, rhythmic shocks. To an isolated accelerometer, these daily actions all produce a sharp, bouncing linear pattern. To the sensor, you could be driving a car or sprinting a marathon. The data looks the same. To filter out this daily noise and lock onto a genuine step, the watch requires an entirely different dimension of spatial awareness. It needs to understand rotation. That rotational awareness comes from the gyroscope. This is the tool required to decrypt the accelerometer's noisy linear signals. Traditional gyroscopes use heavy, spinning brass wheels to maintain orientation in aircraft. Since those cannot fit inside a wearable, the technology had to be reimagined. Modern smartwatches use MEMS, or micro-electromechanical systems. These are microscopic, intricate geometric structures etched directly into silicon. Unlike the static circuits inside a normal computer chip, these silicon masses are physical machinery. While the watch is active, they continuously vibrate at a steady, high frequency. The physical shifts happening inside this sensor are measured in mere micrometers, a fraction of the width of a human hair. By miniaturizing this mechanical system, the watch gains the hardware required to map complex changes in the wrist's orientation through three-dimensional space. The operation of this tiny machine relies on the Coriolis effect. When your wrist turns, the rotation causes those vibrating masses to be pushed slightly off their path. The sensor detects that microscopic deviation and measures the rotation across three specific axes, tilting left and right on the x-axis, pitching forward and back on the y, and twisting around the z. This allows the watch to look for the distinct rotational rhythm of a genuine human stride. A real step includes a forward arm swing, a slight twist of the wrist, and a backward swing, forming a consistent curve. The device continuously overlays this precise rotational map on top of the raw linear data collected by the accelerometer. Machine learning algorithms process hundreds of these combined sensor readings every single second, analyzing swing amplitude and timing to verify the pattern. By using the gyroscope's rotational truth to filter the accelerometer's linear noise, the watch successfully identifies a true step. This three-dimensional awareness gives the watch a vocabulary that extends beyond walking, allowing it to track advanced metrics like running cadence and arm swing efficiency. These two side-by-side graphs show how crucial that data is for strength training. The linear up and down motion of a bicep curl and a shoulder press look nearly identical. But because their rotational patterns diverge, the device can distinguish between them. That same rotational precision drives gesture controls, enabling a quick flick of the wrist to clear a notification or wake the display. The gyroscope transforms the hardware from a simple bouncing sensor into an active, multi-dimensional controller mapped to your body. This capability reaches its highest stakes in the development of fall detection. When a serious fall occurs, the accelerometer registers the sudden, violent linear acceleration toward the ground, followed by the impact. But impact alone isn't enough to trigger an alert. The algorithms require a specific gyroscope signature, the rapid, uncontrollable twisting motion of a human body losing its balance. By combining the linear data of the impact with the rotational data of the fall, the device confirms the catastrophe and triggers a life-saving response. The smartwatch has evolved into a microscopic, AI-driven machine that filters chaotic noise to continuously map your body's journey through space.